Hey, well, thanks for joining me. Today we're going to talk about our last section of this unit, Unit 2, Matter and Energy, and we're going to be dealing with percent composition or compound composition, as well as introduce the mole concept to you. So I think you know that in a sample all the parts have to add up to be 100%. So that's an important idea to keep in our mind. We also know that a percent, such as that on a test, is the number you get right divided by the total. So it's the part divided by the whole, and you multiply by 100. Now it turns out that compounds have fixed compositions. They're not like mixtures where they can vary. Compounds always have the exact same percentage of elements bonded together in them. So as it states here, all samples of a given compound have the same composition. So let's pick a simple example here. Let's pick table salt. Every sample of sodium chloride or table salt tastes the same. It's salty. It melts at the same temperature, and it's also 39.3% sodium and 60.7% chlorine by mass. When we do percent composition or compound composition, it's always by mass. It's never by atoms. Okay? That's really important. I'm going to say that one more time. Compound composition is always by mass, never by atoms. So let's talk about phosgene for a second. It has a chemical formula, COCl2. That's a compound. And even though there's, 2 chlorines, 1 oxygen, and 1 carbon, so there's 4 atoms there, it's 1 out of the 4 are carbon, which is 25%, yet it says it's 12.1% carbon. And again, the reason for that is it's by mass, not atoms. So we're told in this example the percent carbon, the percent oxygen, and the percent chlorine. And if you add those numbers up, you would get pretty much 100%, and you should. Okay? So it says find the number of grams of each element in a 254 gram sample of phosgene. Well, if there were 254 points on a test and you got 71%, you would take 254 times the decimal 0.71 to figure out how many you got right. So in this example, here's our phosgene, in case you're wondering what the structure looks like. These little lines mean a chemical bond, so there's a single bond, and what's called a double bond between the carbon and the oxygen here. So if I want to know how much of that 254 grams of phosgene is carbon, I take the 254 grams times its decimal percent, 0.121. I type that in my calculator and I get approximately 30.7 grams of carbon. If I want to do the oxygen, what am I going to do? You got it. I'm going to take 254 grams times this time 0.162, because that's 16.2% as a decimal. And I'm going to get 41.1 grams. Now, if I want to figure out how much chlorine, I could do it a couple different ways. I could simply take 254, the total, minus 41.1, minus 30.7, and I'd get 182.1. That's probably what I would do. But you could have just as easily taken 254 times 0.717, or 71.7% chlorine, to get the 182.1. That's all you have to do for compound composition. This is showing what is phosgene. I never mentioned that. It would have been a weapon used in World War I. It's a chlorinated compound, and think of it kind of like mustard gas, but even worse, right? Where you can see these poor people dying from inhaling it. You would shoot it out of mortars from your trench into the opposing sides. The problem is they would simply pick up the canister of phosgene and throw it back in your direction, or the wind would shift and you'd probably end up killing as many of your own men as the enemy. So after World War I, mustard gas and phosgene were never used again in warfare. All right, let's try another one. We have this time a sample of butane. Maybe you've got a lighter that you use for your grill at home or something, right? Butane is what they use. C4H10 is the fuel in your little Zippo lighter, or your little lighter. And it says it contains 288 grams of carbon, and 60 grams of hydrogen in this butane sample. Well, that's a pretty big number, I guess. Let's see what it says to do. We want to find the total mass. Well, that's easy. You just add up 288 plus 60. We can do that. We can do that in our calculator, maybe in our head, 348 grams. Next, let's say I want to figure out the percent of each element. Remember at the beginning we said percent is the part divided by the whole. So the part that is carbon would be 288 grams, and what would I divide that by? 348 grams. So the part that's carbon, 288, divided by the whole, 348 grams. Then of course you have to times 100, add a percent sign. So the percent is not 0.828, it's 82.8%. Okay, so we always want to remember you have to multiply that by 100 at the end. And of course, if this is 82.8%, then the hydrogen must be 17.2 because the two have to add up to 100. Or we could have done the part, 60 grams, divided by the whole, 348, and then times 100 to get our 17.2%. So that's how you figure percent composition if you're given the amounts. Now, because compounds always have the same composition, if we were to take a second sample of butane, this time the sample is not 348 grams, but 24.2 grams. And if I want to figure out how much is carbon, I'm going to take the amount times the decimal percent. So this time, the carbon, it'd be 24.2 times, you got it, 0.828. And that comes out to be 20 grams of carbon. Now, I bet you don't even have to use your calculator. Out of that 24.2 grams of butane, how much of it is hydrogen? Yeah, 4.2 grams, because it has to add up to be 24.2. We could have taken 24.2 times the decimal percent, 0.172, and got our 4.2 gram. That's all there is to it, figuring compound composition. When you're doing it, the compound composition in chemistry, it's always by mass, never by atoms. Let's try another one. I got a 550 gram sample of this compound chromium 3 oxide. It has the formula Cr2O3. And out of that 550 grams, 376 of it is chromium. Okay? So that information is given. Then I'm given a question. How many grams of chromium and oxygen are in a 212 gram sample of chromium 3 oxide? Well, let's think about this for a second. If we can figure out the percent chromium in the first sample, how will that compare to the percent chromium in the second sample? Yeah, it's a compound. They have to be the same. So I think that's what we need to do. So let's figure out the percent chromium in the first sample and do that together. So the percent is the part that's chromium, 376, divided by the whole, 550, and then times 100, add a percent. So as a decimal, that would have came out to be 0.684, but I went ahead and added times 100 to get it directly to my percent. Now that I know the percent chromium, and I know that there's only two elements in this compound, the two elements have to add up as a percent to 100, so that must mean that the oxygen has to be 31.6%. I could certainly have calculated that, but in other ways, but I'm just going to leave it the way I have it. Okay. Now, for my sample, the other sample, the one that weighs 212 grams, how much of it's going to be chromium? Well, I'm going to take 212 times, do I multiply it by 68.4? Be careful. No, what do I multiply it by? 0.684. You got it. So 212 times 0.684 is 145 grams of chromium, with the remaining being oxygen. Now, if I want to get the oxygen, I could do this a few ways. I could take 212 minus 145 and get 67. That's probably what I would do. Or I could take the 212, the sample size, times the decimal percent, 0.316. In either case, I'll get 67 grams. All right, I hope that makes sense. You'll have a little homework sheet of practice before the test hopefully that'll make this concept very solid in your mind, and you'll find these are pretty straightforward calculations to get accomplished. All right, and there's what chromium 3 oxide looks like. It's this kind of green powder. All right, we're going to change gears now. We're still going to do calculations, but this time I'm going to introduce the mole concept. So that's a mole. Now, what does that have to do with chemistry? Well, actually, nothing. The mole, although it is an object, it is something. It's really how we measure amount of substance in chemistry. Okay? So the amount of substance, the SI unit for that is a mole. So you're like, what the heck is a mole? Well, it's how we count. Let's talk about it. Atoms are really tiny. They're so darn small, you can't possibly count them. Even if you counted by the dozens or the thousands or even the millions, they're just way, 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 way too small. Look, if you buy grapes, you go to the grocery store, you put the grapes on the counter, the person doesn't pick up and start counting. Let's see, 1, 2, 3, you have 916 grapes there. No, they weigh them, and you are charged by the weight, and basically your pound of grapes has approximately equal to somebody else's pound of grapes. Well, we'll learn that we can actually count moles by weighing atoms. That's pretty cool. So to count atoms, we're going to use this concept called the mole. Now, 1 mole of atoms is actually a very big number. I'm going to write it out for you here. It even makes the national debt of the United States look teeny, teeny, tiny. Right? Still going. Both the debt and the number, I suppose, right? So if you have just 1 mole of atoms, that's how many atoms you have. Now you're looking, you're going, well, that's hundreds, thousands, millions, billions, trillions, quadrillions, septillions, sextillions. I don't know what. I mean, you're making up stuff after that. It's just an incredibly large number. In scientific notation, that would be 6.02 times 10 to the 23rd. Now, it turns out every October 23rd, we celebrate Mole Day. It's a national holiday. It starts at 6:02 a.m. in the morning, and it goes to 6:02 p.m. You look it up, Mole Day, October 23rd. It's a real holiday. We don't get off school for that one, unfortunately. All right, so what do we do with this? Well, let me give you some background on how big is a mole. Right? There's always one person that asks, and I'll say, well, it's about the size of a chipmunk. It weighs about 5 ounces and it has a length about 7 inches. You're like, no, not that mole, but the chemistry mole. Well, how big is 6.02 times 10 to the 23rd? Let me give you some analogies for that. It's big. Okay? If you were to take the average size marble and take 1 mole of them, that's 6.02 times 10 to the 23rd marbles, and dump them on planet Earth, they would cover the entire Earth, including the oceans, to a depth of approximately 2 miles. That's just 1 mole of marbles, and marbles are pretty tiny. Yet 1 mole of atoms could easily fit in the palm of your hand. If you took 1 mole of dollar bills and stacked them face to face, one on top of the other, like I'm showing here, they would go from the sun to Pluto and back 7.5 million times if you had 1 mole of dollar bills. If you were to take a flashlight and put the light at the bottom of that pile of dollar bills and shine it up till it got to the top of that pile of dollar bills, traveling at the speed of light, it would take you almost 10,000 years to travel that distance. That's going at 3 times 10 to the 8th meters per second. Okay? That is an incredible amount of speed there. All right. Now, what are we going to do with this? Well, we're going to do some simple conversion factors, really. Okay? So for every element on the periodic table, 1 mole is equal to the gram mass on the periodic table. So here's a periodic table, an outline of it, and I'm going to pick the noble gases, the ones on the far right, and I'm going to blow those up so we can see them a little better. So we've got helium, neon, argon, krypton, xenon, and radon. So what it says is if you have 6.02 times 10 to the 23rd atoms of helium, they would weigh 4 grams. See this number down here? This is called its molar mass, 4 grams. And I'm just going to the tenths place, 4.0 grams. Okay? That's a pretty easy way to count out 6.02 times 10 to the 23rd atoms. If I wanted 1 mole, or 6.02 times 10 to the 23rd atoms of neon, here's neon, I'd weigh out 20.2 grams. If I wanted 1 mole of argon, I'd weigh out 39.9 grams. If I wanted 1 mole of krypton, 83.8 grams. Xenon, 131.3 grams. So it's really, really a very useful tool, that periodic table, when you have to count atoms up. And of course, if you want to count out 6.02 times 10 to the 23rd atoms of radon, you better record or weigh out 222 grams. All right, let's see what we do next. I'm going to introduce this little mnemonic. I call it the mole island diagram. This will be something that we will build, expand on throughout the year. So right now, it might not be necessary, but we're going to add to this and enrich it and use it all year long. So it's probably worth your time to pay attention. So we've got 3 different things we can convert between: mass, moles, and particles. Now we know that 1 mole always equals the molar mass from the periodic table. So those two, there's our equality. We can use that for a conversion factor. And we also know 1 mole is equal to 6.02 times 10 to the 23rd particles. Now I'm going to personify this a little bit and make this a little more interesting. I'm going to call these destinations that we might visit. So this is Mole Island. And some people like to go skiing in the mountains. So this is Mass Mountain. Think of the MM as molar mass, the mass on the periodic table. And then particle place is my last location. I think of it kind of like a New York City, a big city with lots of things living there. And I'm not just talking the people. If you talk all the cockroaches and everything, it's probably disgusting. It's like 6.02 times 10 to the 23rd living things there, right? But some people like the big city. Some people like going to the mountains. And some people like going to those tropical islands like Mole Island. So let's see how this is going to work out. I wrote this on the top. This is going to be a useful thing. 1 mole always equals the molar mass from the periodic table. 1 mole also equals 6.02 times 10 to the 23rd things. They could be atoms, but they could have just as easily been pencils or eggs or people. So a mole is just like a number, like a dozen. Okay? All right, so let's try this. How many moles is 3.79 times 10 to the 25th atoms of zinc? So the first thing we're going to do is we're going to use that little mnemonic, that little mole island. Remember, mass, moles, and particles down here, right? Or atoms in this case. So where we're trying to go is right here. Red means stop. So that's at what? Moles. How many moles? That's our final destination. Where are we starting? Well, we're given information about atoms of zinc. That's down here. Most of you have had driver's ed or will. Green means go, red means stop. We've got 1 line here, so that means there's going to be 1 conversion factor. So the next step is to write this question as a mathematical statement. How many? If you don't know something, you write X. So how about X moles of zinc? Isn't that what we're trying to find? How many moles of zinc? You bet it is equal to 3.79 times 10 to the 25th atoms of zinc. So I've taken this question and I've converted it into a statement. What am I looking for? Always equal to what do I know? What do I have? Okay? Now, if A equals B and B equals C, then A equals C as well. Now, I don't need molar mass. I don't need that. But I do need to know that 1 mole here is equal to 6.02 times 10 to the 23rd zinc atoms. That's my equality that I'm using. So I put it in here. I need atoms of zinc to cancel, so they need to go on the denominator. Every 6.02 times 10 to the 23rd atoms of zinc is the same thing as 1 mole of zinc. Now notice I wasn't lazy. I included all my numbers with my units, with the material as well. I didn't just write 6.02 times 10 to the 23rd or 6.02 times 10 to the 23rd atoms. I put this many atoms of zinc. Now atoms of zinc up here and down here cancel like that. If I stop now, I would have an answer in moles of zinc. Well, guess what? I want moles of zinc. So now I do the math. This number times 1 divided by what's called Avogadro's number, 6.02 times 10 to the 23rd, and I get my answer, 63 moles of zinc. Pretty good. Let's try another. How many atoms is 0.68 moles of zinc? Now, again, we're using our little mnemonic. This time, we're starting at, look where we're starting. We're starting at moles, because that's what I have information about, and this time we're going to atoms. So this is moles. We're starting there, that means green, and this is atoms, that should be red. So we're starting here, going down here. That appears to be one conversion factor. So let's do exactly what we did the last time. Right, what are we looking for? How many atoms of zinc are equal to 0.68 moles of zinc? I'm looking for a conversion that relates between moles of zinc and atoms of zinc. Look up here. 1 mole is equal to 6.02 times 10 to the 23rd. Which goes in the denominator this time? Well, if we want the units to cancel, we need 1 mole of zinc to go down there, and this time Avogadro's number of atoms of zinc goes on the numerator. Moles of zinc cancel down here and down here like that, and I'm left with atoms of zinc. So I take 0.68 times Avogadro's number, and voila, there's my answer, 4.1 times 10 to the 23rd atoms of zinc. So now we've got that mastered. We can go from the bottom up to the middle and from the middle down to the bottom. Well, let's practice some where we have to go up to mole mass mountain, right? Let's try that. So this says, how many grams is 5.69 moles of uranium? Well, to help us out, we're going to need to look at the periodic table to figure out what 1 mole of uranium weighs. We know the molar mass equals a mole equals Avogadro's number. Well, on the periodic table, there's always going to be at least 2 numbers on the block. The first one is what's called the atomic number. That's the number of protons. That's not what we want. We want the bigger of the 2 numbers, or the one that will have a decimal. The atomic number will never have a decimal. It will always be a whole number. Now, sometimes these numbers will be switched. 238.03 will be on the top, 92 will be on the bottom. So don't base it on location. Just look at the larger number is the mass. So I could fill this in. Every 238 grams of uranium, that number right there, is equal to a mole of uranium, is equal to this number atoms of uranium. Now, if I look at my map, because I don't have a GPS for this, I'm going old school, I'm looking at a map. I'm starting at moles. Well, that's right here. So that's going to be green. And where am I going? How many grams? Isn't that mass mountain up here? So green to red. 1 step, isn't it? So let's write out how many grams, X grams of uranium is equal 5.69 moles of uranium. That's the setup for this question. Now, because I've taken the time to write this out, I'm looking for a conversion between moles of uranium and grams of uranium. Well, look at right here. 1 mole of uranium, 238 grams of uranium. That's what I'm looking for. What do we want to put on the bottom? Grams or moles? Well, moles, of course, because we need moles to cancel. 1 mole of uranium is 238 grams. Moles of uranium here and here cancel like that. So if I take 5.69 times 238 divided by 1, I have my answer, 1,354 grams of uranium. I could have written that in scientific notation if I wanted to have that with 3 sig figs, because it has 4 and 3, so 3 sig figs, the only way to do that would be to write 1.35 times 10 to the third. I guess we could have written 1,350 without a decimal. That would have worked as well. All right, let's try another one. How many grams is 2.65 times 10 to the 23rd atoms of neon? So we know we're going to use this conversion thing. We look at the periodic table to get the mass, the molar mass of neon. Is it 10 or 20.2? 20.2, because it's always the bigger of the two numbers, the molar mass. So now look at this. We're starting at, on our map, we have information about atoms. Isn't that down here? Mm-hmm. And where are we going to? Mass, up here. So that's going to put us green to red. So it looks like we have to go from down here, right? Atoms to moles, that's one step, and then moles to mass, 2 steps. So this is a 2-step problem. Later on I'll show you a way we can do it in 1 step, but that's for frequent flyers. Right now we're going to do what the tourists do and take it in 2 steps. So how many grams, x grams of neon, is equal to 2.65 times 10 to the 23rd atoms of neon? That's the question. We've already determined, because there's 2 lines, there's going to be 2 steps. Now, our first step is going to go from atoms of neon to moles of neon. So 1 mole of neon is this number of atoms. Atoms goes in the denominator, 1 mole in the numerator. Atoms of neon cancel, like that. If we stop now, we'd be stranded metaphorically on Mole Island. We'd be sitting right here. And really, we need to get on another airplane or a boat or something, because we're trying to get to Mass Mountain. So we need another step. How about 1 mole of neon is 20.2 grams? 1 mole of neon is 20.2 grams. Notice that the moles up here and down here cancel this time, like that. The only unit I have left is grams, so I just get to plug it in my calculator. 2.65 times 10 to the 23rd times 1 times 20.2 equals, divide by 6.02 times 10 to the 23rd, 8.9 grams of neon. We're going to try one more. I think it's starting to make sense for you, at least I hope it is. Here we go. How many atoms is 421 grams of promethium? Well, we can start with our map. It doesn't really matter where we start, right? We're starting over here with grams. Where is that? Yep, right here. Isn't this mass? That's in grams. This is moles. And this is atoms. So we're starting at mass and we're going to atoms. So, and here's promethium. It has a molar mass of approximately 145 grams per mole. So this, we're starting up here at grams. From grams we go to moles, and from moles down to atoms. So we set it up. How many atoms of promethium are equal to 421 grams? My conversion factor, my first one, is going to have grams down here, isn't it? Just look at the unit, grams promethium. That means every 145 grams of promethium goes down here is the same as 1 mole of promethium. And grams of promethium cancel. And now I'm sitting here. I went from here down to here. Now I need to go from moles down to atoms. So how about 1 mole is 6.02 times 10 to the 23rd atoms of promethium. And moles of promethium cancel, like that. 421 times 1 times Avogadro's number divided by 145, and there's our answer. Yes, for those of you that are asking, you could have done it in 1 step. If A equals B and B equals C, then A equals C as well. In other words, in 1 step, I could have put 145 grams of promethium on the denominator, and I could have written 6.02 times 10 to the 23rd in the numerator and done it in 1 step. If you want to do it that way, good. If you want to do it in 2 steps, not a problem. You can expect probably 4 of these type questions on the exam when we take that, okay? You will of course have a periodic table provided for you, or I will give you, kind of like I have here, an icon showing you what the molar mass is if you know how to read the little square. I think I gave you a periodic table that you'll always be able to use. I'm not sure, yours looks more like this. This is a nice colored one, but they all work the same. All right, I hope you now know how to calculate percent composition as well as convert between atoms, mass, and the mole. Thanks for watching. Good luck with all your chemistry studies. Bye-bye.